All right, I think I turned this thing on. All right, well, thank you for that introduction, and thank you for the opportunity to come in here and talk to everybody today. I was introduced, Jason Curtsinger. I'm a manager with the Tennessee Valley Authority. For those of you who don't know, we're an electric generating utility that covers Tennessee and the surrounding states. And I don't know if you've been to Broadway or not, but if you look at all the lights and the signs that are all glowing, it takes a lot of electricity to keep this place running. So we definitely have a need out here. But what I'm going to talk to you all today about is a project. And if you will, I'm going to tell you a story. This story, it's going to have highs, it's going to have lows, there's going to be twists and turns, even surprises. But it's about an implosion event that we had. So I'm going to walk you through the implosion, what happened with it, how we set it up. Then we're going to talk about some of our remote exploration activities that we did. And then ultimately we arrived in an innovative felling technique. So that's a little bit of a foreshadowing. The implosion did not go as well as we wanted to. But then also we investigated. We're always trying to strive for continuous improvement, and we wanted to get to the bottom of it. And that's what I'm here to share with you today. So here's the stage that I'm going to set for you all. This is a fossil plant that we were demolishing. Our prime contractor for this work was D.H. Griffin. They're the ones who brought in the blasting contractor and modeling contractor to study the implosion event. I know TVA ourselves, we've imploded over 15 structures alone, and that's not even counting the experience that D.H. Griffin and their blasting team has. I mean, there's hundreds upon hundreds of stacks. So this is something that's, we're all very familiar with. And so here's the project site, and we were planning to implode all 4 of these stacks in one day. So the stack 3 is the tall red and white one there. That was the one that was going to detonate first. And then the second implosion, the second detonation would be the FGD stack. That's the one there with the white tip, and that's that's a scrubber stack. That was built in the mid-2000s, so it's a really common structure these days. And that's the one we're going to be focusing on for this discussion today. So that's the one that was set to fire second. And you can see it was 595 feet tall, which meters-wise, 180 meters ballpark. Sorry I didn't convert to metric for all of our international colleagues here, but I thought about it way too late. But the way we're going to fell these is we're going to drop the first 2 stacks, the stack 3 and the FGD stack, to the southeast there. You see a nice wide open field. And then we were going to fell the Unit 1 and Unit 2 stack right after that into the footprint that we vacated. So that was the plan. Well, how did we get there for the FGD stack? So here's a little bit about the design that we did. So we typically go in and we do a concrete cores to find out the strength of this concrete in the stack. You have historic data, you have some QC records, sometimes if you're lucky. Very rarely do you actually have it. But, and we didn't, even though this was built 20 years ago. So we did some cores, and we took 4 of them. That's pretty standard practice. We'd done that in all of our stacks, and we took them at the 4 cardinal directions, right, along the fall line, took them in the rear where the hinges are about, and we have the strength data there. So our target goal was 4,000 PSI. You can see that 3 of the cylinders came in well above that, but there's one cylinder, S3-3, that came in under. It was almost 1,000, it was over 1,000 PSI lower than our design strength. And if you look, the figure on the right shows the orientation. So the blue section there, where that S3-3 is, that is where the saw cut would be in the back arc. All right, so the green sections in that figure are the hinges, and then all of the red was going to be the part of the bird mouth that gets exploded outwards. And so that's the way it was set up. So I just wanted you to note that one core strength, although it was weaker, it was in the back arc. But if you look at the average values, you averaged out at 6,000 PSI. So we still had a really good concrete strength. And so the team decided to move forward with this information. And we did do a little bit of sensitivity analysis to account for this. Well, here's a little bit more of the design for that FGD stack. This is probably very similar to what you all have seen all kinds of times. We had the bird mouth there. It's about 10 feet above the ground. We built in a little extra there from what we actually needed in order to get the clearance to fall. And then we increased that. We weakened even more concrete on the face. So we had zippers, that's what we called them, and we ran those an additional 10 feet. So all in all, we were weakening the front 20 feet of this stack. So the falling face, we were trying to take out about 20 feet of it, And that's an important number. We're going to come back to that. But the stack itself, like I mentioned earlier, was almost 600 feet tall, but it's 54-foot diameter, so it's a cylinder, right? It's not a tapered one like you see in traditional old-time configurations. This style is easier to construct nowadays, and it's what you all probably have seen go up across the country and across the world, I'm imagining, for these types of technologies. And with that stack diameter of 54 feet, it only needed a wall thickness of 16 inches at the base. So it basically was what we called a thin wall, wide diameter stack. And so that's this category that we're focusing on here. And that's what I'm going to use those terms quite frequently throughout this. But because of the diameter, the fact that it's a cylinder, and the wall thickness, that's how we're referring to it. But we designed the hinge. As everybody knows, that's an extremely critical part of this. And the hinges are designed to take the load of the stack for a very short amount of time until the stack starts falling, and it eventually gets to where you want it to, lay on the ground in that fall line. So what we do at all of our projects is we like to do modeling. We know it helps visualize it, because we oftentimes, these are very public, and a lot of people in our company want to understand what it looks like, right? It's one thing to talk about it, but another thing to see it. And so we've used modeling on all of our implosions. And this one, we had doorways in the bird mouth, so there was additional reinforcement, but we modeled all those doorways, we modeled windows that were in it, and we did vary the strength. We varied the strength from 4,000 to 8,000 PSI, the concrete, because of our core samples, and ultimately, we did expect some drop of the structure. So based on the analysis and the results, we expected the structure to drop about 4 to 8 feet based on the concrete strength. So that was to be expected. The debris field, just like anybody would say whenever you're demolishing a stack like this, it's going to fall, it's going to shoot out. Hopefully it just stays at 645 feet. Hopefully something doesn't fly out 1,000 feet and hit a power line or something like that. But then also, we had a really tight angle. We had a 6-degree cone of deviation from our center line. So that was really good. So we felt really confident that this was going to fall like we needed it to in the zone that we allowed for. And that image there shows what it's supposed to fall like. So this thing is supposed to fall like a traditional tree, the vast majority of these things do. But that's what we ended up coming up with. That was our design, and so we put it into action in the field. So here's going to be the clip. And so in this clip, we've already started with the implosion of stack 3, and it's going to start falling. And then we detonate the FGD stack. So you want to pay a particular attention on the back side of that stack. You see the black rectangle there? That's the breaching duct. Now, when you watch this, look how far down that breaching drops. Now, remember, we only thought it was supposed to drop 4 to 8 feet, but watch how far it drops and how quickly it drops. And I don't have any sound. This is just raw drone footage. All right. Hopefully you guys were able to see that. I couldn't tell. My screen was glitching a little bit, but hopefully you were able to catch the gist of it. But basically, that stack, it dropped and stopped. All right, and it dropped a significant amount. You saw that breaching duct fall a long way. So I was standing in the viewing area, and when I saw this, I was like, oh no, this is a very low thing, right? And so what was even more heartbreaking was this next video. So we had drones everywhere because people like implosions, and we like to cut together good, cool videos. And this one was taken from the top. So just watch the motion of the stack in this particular shot. So it started traveling, and then it stood back up and kind of wobbled into place. I saw some dance moves like that at the honky tonks last night. Sure, it might have been my own, but that's neither here nor there. But no, when I saw this video, it showed how close we were. That stack was on its way, and then it stopped. And it's like, why did it do that? How did it do that? All kinds of questions were running through our head. But this is the condition that it was left in after this implosion. So we made the decision to go ahead and detonate stacks 1 and 2, and they missed it by mere feet. The ends of those stacks, you can see the debris field there runs right along the top part of the stack here, and we missed it. But the vibrations, the impact vibrations, didn't cause the stack to fall down either. So, get scratching our head a little bit more. It's kind of like, all right, what's going on? And we put that little scale up there, that protractor, to show you this thing was about 2 degrees off of vertical. So this was something where you stand back, you can see this. And here's a little silver lining about this whole incident, is we spurred the local economy on. There's a little distillery near this site, and foot traffic increased tenfold because people could take good pictures. You're sitting there holding it up, propping it up, all that good stuff. And so the locals started calling it the Leaning Tower of TVA. So there's worse things to be known for, I guess. But that's where the condition it was left in. So here's a picture closer up of the bottom of the stack. This was the falling face. So you can see it is in pretty good condition on the outside. There's that one pretty good crack right there in the middle. But I want you to pay attention, particular attention to the rebar. You see all the rebar around the base. It's sticking up, it's curved. It's blocking 7, 8, 9 feet of the front of the stack. So it's inaccessible, really, to get through there unless you go in and remove all the rebar, unless you remove all the debris. And so ultimately, we figured out that the stack dropped 22 feet. You think back to our zipper height of 20 feet, this thing, it dropped all the way down to where we had weakened the concrete and then stopped. And then our lean was like 2 degrees off, like I said. But then the top of it, where it finished at, it was 15 feet. It had moved 15 feet from the vertical. And then we did a calculation, because the first thing we wanted to know is, hey, will a windstorm pick up and blow this thing over? That was our concern, because this was an active site, and we wanted to know if there was a chance of this thing just randomly falling over with people, not in the fall area, but there's a switch yard nearby where they might be doing work. There's a couple gas plants. And so we did a conservative calculation, and we came up with 35 miles an hour. Now, that's awful conservative, but we don't know the condition of the concrete on the inside of the stack. We can see here, it's bedded on rubble, concrete, and all that. And so we were a little cautious. So if we had notification alerts to where, hey, if speeds are going to be this high, we need to have eyes on it. And then the center of gravity shifted 9 feet. So this thing, it was so close. It was so close to going, but it didn't make it. And just for comparison purposes, the Leaning Tower of Pisa is just 4 degrees from the vertical. But we're 3 times taller, so it's kind of a balancing act, right? All right, so now we knew we needed information. And one of the first things that we did was we set up a monitoring program to see if this thing is starting to shift and fall. Because any option that we did to try to bring this down, we would need to be able to track that. Well, we initially started out trying to use a total station, and we ended up trying to just measure it off of ports and steel that were on the stack. But the wind would play havoc with that. The thermal expansion and contraction of the concrete every day, it was really hard to use that. And so we came up with the idea that we needed to set some prisms on there so we could use robotic total stations. If we had 2 of them on there, we would have very accurate numbers. We'd be able to track this thing if it moved, and we would be able to get real-time alerts as this thing was moving. You didn't rely on somebody looking through a lens at it. And so we learned about 4 or 5 ways to not install a prism on the stack. We had a few failures. We only had 1 crash, but that's okay. But ultimately, they were able to figure it out. The site team did a great job. They persevered, and they just stuck a little piece of metal sleeve there with epoxy on it, and stuck the prism, and they flew it up with a drone. And you can see on the left picture there, that's a very engineered device right there, the top of the line. But we got them in place, and that was extremely important because we were able to track the movement of it as day by day, but also when we started to fell it. We also needed to get some updated survey information. So everybody's used LiDAR on the drones, right? That's something that's pretty common to use. We did it. And then it gave us some great data. But then the TVA has this robotic survey device. You all may have seen these things. We call it Spot. I hate Spot. I wanted him to stay in front of the stack and get squashed because I think he's creepy. But that's beside the point. But you can see down at the bottom, we used them to get a little closer picture of the rebar, what the debris looked like around the bottom. And you can see in that point cloud there, there's a lot of rebar sticking up. You can see the debris. And so we were able to mesh all that together. And we had the best model that we could possibly have to go forward with. And this is where, with D.H. Griffin's fleet of vehicles, we were thinking outside the box. We were thinking about blasting. That was, hey, we can blast this thing down. Well, with the height of the rebar, your typical drills that go on your skid steers, they can't reach high enough. And so D.H. Griffin luckily had a remote-controlled excavator in their fleet, and they were able to bring it out. And it's just like the setup you all see out here in the hallway, where it's the operator's chair with the TVs. It's got cameras on the machine. And we gave it a few trial runs. We gave it some tasks with the operator to go out there to see how well this thing would work, see if it was a possibility. So first we started cleaning debris around the stack. That went really well. The only thing we found out, though, was line of sight was extremely important. There was blind areas around the stack, and so we had to readjust our trailer positioning, ultimately, to get the best signal. And you can see here, the bottom picture, that was the typical drill you would use. And they mounted it on the excavator. So they made the attachment, because we had a proof of concept, right? If we wanted to drill these holes, it had to hit a target, because every drill pattern has to be pretty accurate, and it has to get the right depth, right? Well, we were able to hit the target, the dots that we painted on there, but we couldn't get this pressure to get any further than about 6 inches in. So that was a really good idea, and it got the creative juices going, but unfortunately, it didn't pan out. But then we wanted to know what was on the inside, right? Because if we're drilling a hole in there to put dynamite, we want to know if the inside is in good condition. Otherwise, it would just break through, and you would lose a lot of your blast power. And so we had a track-hoe attachment for it, too. And so with that, we were able to punch a hole in the back, and that showed proof of concept the hammer could work with this. And I'll have some pictures from the inside that we took later in this presentation. But because the hammer was working so well, it got us thinking, hey, we back in the day, well, I think it still happens, and I learned this for this project, is that for shorter stacks, or silos, 200 to 300 feet, they'll use excavators to bust out the eyebrow and then come around and cut the back and let it fall. And so we got to thinking, it's like, hey, could we do that with this robotic machine, with this remote control machine? And so the left picture here shows where we had to end up setting up the trailer. And you can see it's to the left of the stack. That gave us the closest or the best line of sight to the front of the stack, because once that machine lost signal, it stopped. There was no moving, it just sat there. So what if we were using this thing to fill it, and it broke and it lost signal and the stack fell on top of it? That would be a really bad day. So we worked with the engineering on this big time. That pattern you see there, the eyebrow shape, that's what the shape is that we decided, working with the modeling and all the calculations, that would fell the structure, but it's set up a specific way. So you see the orange and the green sections. They're on the right half of that. The middle point is the center line of the fall. So based on the engineering analysis and modeling, we would be able to do the orange section, we'd be able to do the green section, and the stack would still stand. And then whenever you got to the magenta section is when it should start to fall. But if you didn't get it to fall in the magenta, you would just carry through the red all the way to the ground. That was the design behind this. And that was really helpful, because with that stack starting to fall with the machine on the west side of it, it's got a lot clearer path to get away. And we did some time trials with it just to understand how fast it would go, and it covers 50 feet in about 14 seconds. So it's not terribly fast, but hey, it's better than nothing, right? But this was the pattern, and with the excavator, we could set it up higher than the rebar, and that would work. So we had to make a decision. And we had these two main ideas here. Blasting was one of them, and the remote operated excavator was the other. So with blasting, the blasting contractor had a stack squat, and they were successfully able to bring it down, drilling holes, blasting it. So we had a proven theory, or not more than a theory. We had a proven way to do it. The new blasting sequence, given the angle of the lean and everything, it would work. The modeling showed it would work and would keep falling. And we did have if for some reason we're out there and we're doing this work and the stack started leaning, we'd be able to pull the plug, bring in this remote excavator as a backup plan. So we had a plan B that we could do if we wanted to. However, there was a few drawbacks to it, and because of the height, we would have to use man baskets to drill the holes, to do the loading and tying all the deck cord, and that's slow. Man baskets are slow. If you started seeing that stack fall, it would be hard to get a man basket out of the way. And then when you looked at the number of holes that were required and the patterns, it was about 3 to 4 days worth of work. So that would be 3 to 4 days of people working in man baskets in front of a leaning stack, which was, that carries a risk with it. And then you would have the people working in the shadow of the stack, but then also, as everybody in here knows, implosions attract a lot of attention. There would be extra site protocols. We have to do security, more coordination, and it's a big to-do. Well, the remote operated excavator, when we started doing the pros and cons there, it eliminated the need of personnel working in the stack. It took we estimated about 30 minutes for somebody to go up there and paint this pattern, so the operator would be able to follow it with the machine, but that's it. And then the activity itself would only take 2 or 3 hours to actually chip out the eyebrow and get the stack to fall over. So that's a pretty quick process. And then it's not an implosion, just mechanical felling, so there's not all the hoopla, not all the bells and whistles associated with it. And then the modeling showed the hammering sequence would fell the stack too. But some of the cons were, this relies on that radio signal connection. Like I mentioned, it was pretty finicky. We found that the police radios on site would interfere with it, so we had to have all our police people turn their radios off. It was a risk, especially if that started falling and you lost signal. That machine was done. And of course, the damage to the machine. We could smash that machine. It was a Cat 336 that was equipped with this. So it was it's not the most elaborate piece of equipment, but I don't think anybody in here wants to just sacrifice one of those. And then if this thing broke down, say we had a catastrophic failure out there, it would take several weeks to get a replacement machine. Not the machine itself, those are in big supply, but getting the remote control abilities hooked up and set up. That would be the hard part. So these were what our pros and cons were. This is where it came down to decisions. And ultimately, it was selected to go with the remote operated option with the excavator. It basically eliminated safety risk to personnel, and we were by using technology. It's kind of coincidental we had that panel about technology and demolition right before this, but we decided to leverage the technology in order to fell this stack. Okay, so now this is the suspenseful part of the presentation. So the excavator is down there in the bottom, and I'm going to ask you to pay close attention to the actual concrete as this video progresses. But do we want to do a raise of hands here? Who thinks it's going to make it out, or who thinks it's going to get squashed? So if you think it's going to get squashed, raise your hand. Okay, we got a couple. We got a few. All right. But with that, I'll play the video. And that's it. We were able to fell the stack successfully. It went without a hitch, and there was a couple times it had to come over to get the mechanic to tighten something here or there, but in all reality, it went off without a hitch, and it got the structure down. And I will say it was extremely loud because it had a stainless steel liner that was hung, and it crushed it. It was one of the loudest things I've ever heard in my life. But the machine got away in plenty of time. Did you notice how the concrete started cracking and shot the rest of that eyebrow out through the pattern? We didn't expect that, but that's what ended up happening, is it finished the rest of the pattern, and as soon as the operator saw that start to take off, that was a clear indicator. He turned and ran. So that gave us that extra time we needed to get clear of it. I think the only thing that possibly could have hurt it was he ended up running over an I-beam on the way out, but that's it. So we successfully felled this. And to the best of my knowledge, this was the tallest one that they've ever done with this technology. And it was a raging success. Now, the engineer in me, we have to do an investigation. We want to know what happened. We want to know why this happened. How do we stop this from happening in the future, right? And I'm sure everybody in here would kind of want to know what we came to as well. And so we had this list of things we wanted to do, and we needed to review the QA/QC information. That's something that was the easy, hey, we need to do this, right? We hired a third-party engineering firm to come in and review all of the design that we did. They were actually helping with the design of the eyebrow and all that too. And then we ended up having extremely great coordination between the demolition contractor, the implosion designer, and the implosion modelers, and the third party. And they shared information freely and models freely. I have to say, I'm really proud of the way the team worked together. This could have been a time where everybody turtled up and didn't help, but the team worked flawlessly through this. And of course, there was calculation after calculation after calculation with finite element models, but also hand calculations. So we were trying to truth our models because the model showed it was going to fall, but it didn't. All right, so we're going to dive into this now. And this is the QA/QC. So this is the QA/QC spreadsheet that Griffin used. I give it to him it's a very detailed sheet, and it covers all kinds of tasks. Like, did you cut your wedges? Are your holes drilled? Did somebody check the hole depth? Is the pattern right? But there's a checkoff for everybody, because you only get one shot at this, right? You can't go back in after the fact and say, oh, did we put all of the dynamite in? Was everything tied? Did we make all the right cuts? That's only, once that ignition goes off, you can't do that anymore. But because of the great documentation that they had, the rigorous QC checks that they had, and the pictures and the videos, we were able to go back quickly and review the design and the implementation, and it was done correctly. So there wasn't a miss. There wasn't a miss in the design or the actual implementation of the design. That moves us on to the second, where we start looking at did the tower behave how we thought? Was there something crazy here that we didn't know? So this is a table here that was created. We used some energy method calculations, and these were the hand calculations that we did. And we used the actual data from the videos, because we had time and we had distances that we could figure out from it. So we were able to come up with angular velocities and track those. And the importance of angular velocities is you want the stack to get that motion going. You want it to start falling like a tree. You want that angular velocity to increase to the point where it doesn't stop. You don't want it to stop like it did for us, but it's a race. You need that to happen before it crushes to the ground and squats like what we saw here. And so the purple line here, that is the vertical displacement of the stack itself. So you see about 2 seconds after the implosion, it started its drop, but it did not stop. It just kept dropping all the way down to that 22-foot mark. So in just over a second, it had done all the dropping it was going to do, and we'll need to pay attention to that for the other couple lines here I'm about to talk about, because the orange line, or no, we're going to talk about the orange line. That was the green line, sorry. I got them mixed up. But no, the green line is the horizontal displacement of the top. So we were able to measure what that should have been, or what that was in the videos, the horizontal displacement. And then we used the calculations to determine what it should have been in theory, right? And so we overlaid the theoretical versus the actual data that we had. And you can see there on the green, they follow each other up really close until about 2.5 seconds. And if you note, that's when that drop, just after the drop had started. So that drop was the reason why the displacements started diverting. And so then with the displacements, we're able to back into the angular velocities, and that's what the orange lines are. So you see that the actual, we calculated that using the actual distances, and then the solid line, that's the theoretical. And you can see they're almost spot on, right? You lay those on top of each other, and they carry on through up until about 3 seconds, which is shortly after the stack started dropping. And that's when they start diverging. So that stack drop is what ended up causing a lot of divergence. But the good thing is that what we thought should happen with the stack aligned extremely close with what actually happened until the large drop. So we were on base. We were on the right track with that. All right, so now we're looking at the hinges. We moved to those. So this is the model, or one of the models, because we had the implosion modeler had their proprietary software, and then our third party, they had their proprietary software. So we were running 2 of every model to compare. And so this is one of the models here. And it's hard to see in the first, but that's 1,000 milliseconds. So 500 milliseconds is whenever the shot happened, whenever the implosion went off. So in half a second, that green, in the very bottom corner is the picture of the hinges. So they're split left side, right side. And the red in there, that's 5,000 to 6,000 PSI. So that right there is approaching, if not higher than, the strength of the concrete. And you see, half a second into this, we already see red in our hinges, which you would expect. But it only gets worse. So you follow the progression. So you go to 1250, and you go down to 2000. You see the red just keeps growing and growing and takes up more of the hinge, right? Well, when you get down there to the 2500 millisecond, the bottom left one there, you see all red on one hinge, but nothing on the other. That hinge has failed. That hinge is gone. It's carrying nothing. And then shortly after that, that other hinge fails. So that's something that we expected to occur. And you have to have your hinges fail, otherwise your stack will continue to stand, right? It's not something that you want to happen. But we realized that we had a lot of stresses really fast in those hinges, and that drop would have occurred in that ballpark, right? That would have caused that drop to occur quickly. So one of the models we were running with, it showed rebar. And here's where I was going to refer you back to the beginning whenever we were looking at the rebar around the base and how it's curved. You can see the pictures of the model here. It shows the rebar curved on the outside like it was going in, and we saw that on the real life stack. And then the bottom picture, you can even see more clearly. That's a picture from the inside of the stack. You can see the curled rebar there. And you can see in the model, they had curled rebar there. So our model was showing the rebar, it matched up pretty well with what was going on in the field. So, we're feeling good. We're checking all these boxes off, right? Well, the interesting thing is the both models showed the stack failing regardless of whatever scenario we changed. One of them would fall like a tree, and the other one would telescope down. So they failed in two different mechanisms, even though they're analyzing the same stack, right? So that was really interesting. We're scratching our head about that. It was a little confusing. But here's a table that shows some of the runs and analysis we did. So we changed the back strength of the concrete wall to 2.9 KSI because that's what our concrete core, but it still stood up. Or no, it still failed. We changed all the concrete in the whole stack, all the way up to 3,000 PSI. And it still dropped, like the model said, but that didn't happen in real life. And we varied the strength of the concrete. We changed some of the algorithms in the program. We even thought, because this was loaded on the inside of the stack, we thought the blast pressures might have caused some damage to that back wall. And we modeled that, and it still fell to the ground. So we couldn't get it to mimic the field conditions and get that big drop. So that really left us scratching our heads there. So we had to get to thinking, so what are we missing? Our models, they're matching up with some elements. But they're not modeling what we're seeing in real life. So we ended up thinking about it, and something that we're missing is as that was crushing, as it was dropping, it has to crush the concrete. It has to break the rebar that is going through. And on the front side, if you remember, we had 10 foot of zipper. So we weakened the zipper parts, but there was still concrete in those front and between those zippers. And so what we ended up doing was the one model is this one did account for the energy dissipation with the concrete crushing in the back. But what it ended up doing was it immediately removed it from the model. And so we had to go into the model, and we had to edit the back wall strength to about 3,000 PSI. And then we added extra blocks to simulate crushing concrete and rebar that might have been accumulated, or maybe that wasn't fully blasted out. And we were able to model that, and it did stand up. We did get the lean of the structure in the model, and it stopped. And it was close to what we saw in real life. So that was really good. We got one model to mimic what we saw in the field. Well, we had to go on to the second model to see if we can duplicate it. And turns out we were able to. In this program, they were able to add an external damping factor, which ultimately, once the element crushed, it would go away from the model, but this damping allowed it to stay in and interact with the model. And because we had video, we knew when this occurred, when it started dropping, we were able to set this damping factor in there. And you can see here that chart. So the red line, that's the lateral movement of the stack, of the top of it. And it came up with it being 12 feet. If you remember earlier, it was 15 feet is ultimately what we saw in the field. So that's really close. And then for the vertical displacement, this model, the black line, it shows it would drop 23 feet. It dropped 22 feet in real life. And the model ended up standing at that lean. So we were able to get both models to the point where they mimicked what we saw in the field. And so that gave us some good information there. Now what we're trying to do is we're like, hey, what would be a great idea here is if we had a quick, easy rule of thumb that we could use whenever we have a stack. We can say, hey, we can do a quick calculation and say, hey, this is a metric we can look at to say, is it going to be a risk of squatting or not? And so we worked with our blast designer and the engineer there, and he worked on 56 projects up to this one. And so he had all kinds of data. He had metrics like diameters and wall thicknesses and rebar spacings and all that. And so he was able to do a lot of stress calculations. And we had a whole database, basically. And the team decided there was two scenarios we thought would be the most helpful. One would be the concrete stress from overturning on the hinges. So you can compare that, the overturning moment on the hinges to the concrete strength and come up with a real quick ratio. I included our numbers in here just in case you wanted to ever use them as like a truth check. Maybe you ran that and you saw you're at like 17. You might be like, oh, something could be going on here. But the other scenario was the concrete stress overturning moment on the full back arc. And so that ratio is obviously smaller because you have more area to distribute the weight. What's unfortunate, though, is that after review of all 56 of these, we spliced the data, we looked at it a whole different bunch of ways, and we couldn't find any clear correlation to make a rule of thumb. And so, that was really disappointing. But we decided to break it down even further. So this engineer, he had worked on 4 thin-walled, wide diameter stacks up to this point. And so we compared them to those 4, and we still couldn't come up with a correlation. So unfortunately, we can't just say, hey, if you got a 2.7, you're good, unfortunately. But we tried. But it was a really great exercise. We were hopeful, but in the end, it didn't work out. So to summarize the analysis that we did confirm that the original implosion calculations, it should have fallen using the standard typical level of care in the industry. So, we didn't miss something. We did everything we should have. It just didn't turn out the way we wanted to. We did learn the overstressing of the hinges occurred, but it's typical in implosion. But we also did learn the stack should have had enough kinetic energy to keep falling. It should have been able to keep falling over. But because there's assumptions you have to make when you're doing these calculations, you could modify some of these assumptions, and it may not fall over. But it's really hard to know because you could tinker with this for years, and you never match up those scenarios. One other interesting fact was the concrete strength in that back arc from the numbers should have been adequate to hold that stack up to keep it from dropping. One of the theories that we had as to why it didn't was as it started to tilt, it's going to experience a lot of different pressures and forces that you just can't model, and we think that might have caused buckling of that rear wall. So when those hinges did crush, it ended up causing that back wall to crush too and give way. The big thing was with the finite element models was that both of them needed a secondary mechanism in order to dissipate the energy to observe our conditions. So that's something that is not standard. That's something that it's hard to guess at even. You could guess, but it could be really a wild guess. So it's really hard to do. But it's believed that the crushing of the rebar and the concrete is what led us to losing a lot of that energy, to dissipating a lot of it. Another positive thing is that we found the finite element models and our hand calculations, the stresses were really consistent. So we were able to do check after check, and we were able to prove that, hey, we were doing this correctly. So that gave us some comfort level with our analysis. And unfortunately, like I mentioned, we could not determine a rule of thumb for the key stack parameters. That would have been great. But in general, our lessons learned boiled down to these thin-walled, wide-diameter stacks. They should be evaluated with extra rigor. It's something that's new to the industry as far as they're in the newer plants, right? They're newer construction, and so they haven't been brought down. There's not decades and decades and decades upon experience. And we learned real quick to obtain more concrete core samples. We're shooting for 4.25, but take them at different elevations, right? These things are made in rings, and one ring could be strong, one could be weak. It's something that you all should really consider doing. I know TVA, we're doing 4.25, and it's been really helpful. It's been surprising what we've been able to find out in some of our stacks we've imploded since. You can also consider performing some of these additional modeling scenarios with this mechanism to dissipate the energy. That's something you could try to do and see if squatting is a possibility or not. And then the best thing to do is when you're doing your blast design, just be a little bit more robust in that design. And here are some ideas that were pulled together. And for the blast design in particular, a finer hole pattern, you use more explosives, but it'll demolish the concrete more efficiently, right? It could damage the steel more and do a more thorough job. You could raise your eyebrow higher. You're weakening more of that front face. And that goes with the taller zippers. It continues to weaken the front of the face. We feel like if we would have gone up just a few more feet, this stack would have just kept on going over, and I wouldn't be standing up here talking to you today about this. But then something else that you could do is additional openings above the leading face. So in theory, what this would do is you would have your eyebrow, you would have your zippers, and then you would have a higher up hole. So when that started falling, should the hoop strength in the cylinder or the stack take over and it stop falling, it would break along that upper hole you cut. So it would continue to fall. And it wouldn't be stuck in we successfully dropped our stack 22 feet. You don't want that to be your story, all right? But then also around the stack openings, we used steel beams. We inserted them in there and installed them, but we were also looking at using a reinforced concrete because that would hold better. It would be one less thing that could go wrong with the blast pressure. It could knock it out potentially or tilt, and it could weaken your supporting surfaces. But then with the door jambs that we have in there, they make thicker rebar clusters. And so making sure to saw cut around door jambs, that's one thing to do for sure. And this stitch cutting, this was an interesting concept that we used where around the eyebrow is your engineer would have to design it, but you just cut like 2 or 3 foot long sections of the concrete just every once in a while. It looks like somebody did stitches along the front of the stack. That way you're making sure you get rid of the rebar that could be stuck in there. But the hinge design is something that is extremely important because the longer that holds up, the further it falls in the direction you want and the better results you're going to get. And so you can reinforce the hinges with steel plates or Dowden reinforced concrete stiffeners. And that provides the strength to help resist premature crushing. Now, I do have all these lessons up here, all these design improvements. I have that disclaimer at the bottom. Note that these are all just consideration only. Each stack is very unique, and everybody should do their own job of thoroughly evaluating it. So I have to say that legally, I believe. But I just wanted to make sure that was said. Each one of these things is unique. I know we had a very experienced team, and this was the luck of the draw this time. Now, I will say, I did give this presentation earlier this year, back in February, and since then, I know of 2 of these stacks that are similar style to this. One of them, it was implemented with higher eyebrows, higher zippers. They used concrete stiffeners. They basically poured a concrete wall on the hinges and on the back arc, and they dowed it in, and that went flawlessly. And it was a very high-profile implosion event. I know they're all high-profile, but this was in a very populated area in a neighborhood, and it went off without a hitch. That was a great win for that team. Another site, they had a similar stack, and they ended up using steel plates. I know that's I've heard it called the Oreo effect. You sandwich it in there, and you just dowel it together. And in that project, there was a building nearby, 30 feet away they had to keep. There was other sensitive infrastructure that couldn't be landed on. And turns out they drilled a bunch of extra core holes, and they found one hinge was a lot weaker than the other. So had they not done this extra work, they wouldn't have realized the strength differences, and it could have tilted towards the sensitive infrastructure. So I just want to say those were a couple of real-life examples where people implemented these lessons learned and came away successful. But with that, I'm going to turn it open for questions, but I will say I'm a geotechnical engineer. I'm not a structural engineer. So if your questions are really detailed or complicated, I may not be the person to answer them. But this is the excavator that we used with the operator and the mechanic as well.
Hi there, Richard Van from RVA. Great presentation, really enjoyable. Thank you very much for that. Just a question. You are, I guess, representing the owner of an asset, an operator, and interesting approach to the way you've managed this, which I'm very impressed with. But the responsibilities and the lines of liabilities between the client and the contractor, because of all the work that you and your team have put in, must have become quite blurred at times, and where the onus of if this works or it doesn't work, you know, quite frankly, who carries the can for all this lot? And you know, you've approached it, it seems, as a very much a cooperative team to do this. But how did that sit with, you know, your organization, insurers, and et cetera, et cetera?
Yeah. Well, I mean, that's a really great question, and I can understand that being there. And I will have to say the team was extremely collaborative. Everybody worked together. I know through the way our contracts are set up, we have the prime, and you know they're responsible for the subs. But I'm not really going to get into all the specifics of that because I'm not willing to share that. Yeah. So I don't. Yeah. Oh, that's fine.
Any other questions? Did we have one over here?
Just curious, as a related agency within the federal government, was there any serious discussion at any point of using military artillery to take out the base?
That's a good question. There wasn't a base nearby. Yeah, well, it was floated out there, but we couldn't give them the exclusion zone that they needed. So it was an option, but it wasn't selected.
I have one other question. Communication with the client through this process must have been difficult at times. How did you manage that side of it?
Well, I'll have to say that Gene and his team, they did a great job with that. We had routine meetings. There was daily emails because obviously the CEO was going to be very interested in this, so emails were getting put together daily, and they was communicated all the way up to the top of the chain. But we had calls very frequently. If there was ever a time whenever there was a question, we didn't hesitate. We knew this thing was in a precarious situation. I mean, there's people working on Saturdays, Sundays, working way into the night, and we met as groups at least once a week, sometimes twice a week as the larger group. So we had a great flow of communication, and it was call somebody up if you needed to, and it worked itself out. All in all, from when the implosion happened, we brought it down 3 weeks later is when we did.
Yeah, it's Patrick Fry from Cardem in France. It's not going to be a question, but a comment. I really want to thank you for sharing this, and I think I can speak for the name of many contractors here. Thank you.
Yeah, you're quite welcome.
And once again, thank you for sharing this project, Jason. Sorry.
Just a quick, Wayne Bagnall, yeah, UK, standby speaker. Really good to see you there. Just wanted to say, Jason, we've all had projects like this go wrong, and I can remember one in the 90s, and it didn't do that. It went at an angle, and the sergeant who was stood next to me said, "That went wrong." I said, "No, that's stage one." He said, "Really?" I said, "No, not really." And we had to use non-hydraulic mechanical attachments, whereas you used a remote mechanical excavator with a breaker. So well done, and really applaud that you share these things, because things do go wrong. Everybody in this room knows that. And I think it's good of you to share that. So well done.
Yeah, thank you. It was my pleasure.